Waiting it for. Okay. All right. So, in a practical implementation, instead of C inverse X for whatever vector X you need to use it with, that would be the same as, let's see, LUX. All right, let me make sure I have a correct order here. So that'd be the same as, okay, so LUX, so L inverse times U inverse. Okay, so U inverse L inverse X. Because you wouldn't want to compute the inverses of these explicitly either. So you can do that. Okay. So once I formed C, then what I ran was this with that C passed as a preconditioner. Okay. Oh, you know what? I passed the wrong right-hand side. Oh, that shouldn't matter because right-hand side is random anyway. But I should have put the original right-hand side here. But it is the original matrix. Now, as far as your code is concerned, I had to make a few changes there. Okay. Well, okay. So let's see. Oh, yeah. So here I'm updating Z in the same way. This is something I told you about in the email.
Yeah.
Okay, and then okay, so then I have this relationship to update your U vectors. So that way this will take care of the V's.
So what exactly did I do wrong? Why wasn't I looking at my own?
Oh, okay. Hold on. I'm gonna make a backup of this file. And then I'll need to re-download your original one. Do I have that? Oh, no, I don't have it here. Wait. Okay. Wait a minute. I thought I. Oh, okay. Okay. All right. So here's what you sent. Now, actually, it might be enough. Okay, so this has to be. All right, so that needs to be Z.
Yeah, I fixed that.
I wonder if that might be enough. I'm gonna try it on that, and no other change. Okay. Oh, okay. Whereas if I run it on 2, okay. Okay, that's. I was going to do a comparison here. Okay, there's no other difference here. All right, so now if I go here. Okay. Oh, okay, so y times. All right, here I have r and u. You have y and z, but I believe those are equivalent. Okay. I need to see if there's anything else that's different. Okay, so x, r. All right, yeah, because that's different, but it's still correct. And as for the betas, y, z, well, okay, let me try this. Okay, RU versus Y and Z. Let's just see if that makes the difference. That did not help. Okay. Wait. Y, Z, Y, Z. Okay. All right. Now, okay. If I update, okay. All of those are the same. Wait, PWV, ZYU, PWV, ZYU. Okay, these are the same. Now, if I instead update Z in the same way that R is updated, then this needs to be equal to C inverse times W. Or yeah.
That's, I think, VI.
Yes. So if I do that and then comment this out, okay. All right, and then YZ, okay. Okay, what else is different? Okay. YZ, WB. So yeah, okay, if I get rid of that, yi plus 1 is, oh, that, I plus 1. Okay. There you go. Converges right away. So, all right. Okay, now I'm going to put this back the way it was. So now imagine exactly what you said me before. Okay, fix that. But then this has to be zi plus 1. So z has to be updated before y is. So then, let's see if that works. Okay, so this is all that had to change from what you sent me before. Only that line, and because it relies on zi plus 1, z needs to be updated before y is.
Okay. Okay.
Okay. Well, okay, so I need to. I think. Let me check here. Here's the. Okay, I need to send you this. This is the stripped down template.
Okay.
Okay. All right.
So, like we said a lot of things now, more like a summary. What's the next step apart from trying to get some writing done? What's the next step for this code? Like,
Okay, so yeah, I guess try to have like a few different examples that hopefully show good results like this. Now, but the thing is, I want to take a look at the preconditioner. Now this one used okay. All right, so that was done here using R. Okay, so that relies on a Cholesky factorization.
yeah.
So see if this could be, now if you look at the help page for incomplete Cholesky, if it's something I had some trouble with, here's how you use iTrol, where you set some options as far as like dropping certain entries and things like that. So we should see if it's possible to get this to work. Because that way, this is something that'd be more practical. Like, okay, we're not doing a full Cholesky, but a incomplete Cholesky. And then using that as the R in here. And what I'm hoping is that, yes, it'll still converge fairly rapidly, not that rapidly, but yeah.
Okay.
So for example, if we set a drop tolerance, how does that affect the performance? What I don't understand is when I tried using this on a matrix where A is symmetric positive definite, why an incomplete Cholesky would fail. I don't know if it's because of it having to be a bad example or what. Now, I wonder if this might be a good idea. Using compensated incomplete Cholesky. That way it might be that would cause A to have this matrix, if it's Cholesky factorized, to have a larger diagonal. And maybe that would make it succeed where a previous one failed. Let's see. If I take, because you're computing a Cholesky factor of Okay, B. So what would happen, like, if I do something like that? To drop tolerance, and then all right, I gotta force it to be sparse. Oh, okay, so it worked in that case. All right, so that's good. So that's, but oh, okay, so that's now if I do the true Cholesky factorization. All right, so there's a true Cholesky factor, and then the incomplete Cholesky factor. Are they the same? Oh, they are the same. Okay, I don't like that. Oh, I guess the drop tolerance is only used with okay, type of factorization. So drop tolerance for ICT. Okay, so I need to specify that. Okay, so okay, so it still worked. But the factors are again the same. But I specified a drop tolerance. Okay. 10 to the minus. Okay, so okay. Drop tol. Elements of smaller magnitude than a local drop tolerance, except diagonal was never dropped. Okay. All right. Yeah, but that's what I wanted. If I look at B, oh yes, this B is not sparse. Oh, but maybe because there are no particularly small entries except for ones that are already 0. Maybe that's why. Okay. All right. If I do, I can change this to 0.1 to make B sparse. If I look at B, B is now sparse. All right, so there's my Cholesky factor. There's my true Cholesky factor. And once again, they're the same. But at least it's somewhat sparse. Okay, that's kind of strange. Maybe if I set a different drop tolerance. Still the same. Oh, now they're different. I guess if you yeah, like that entry is missing, and Yeah. Okay. And these entries are different. So, okay. So if you set a large enough drop tolerance, you can get them to be different. Um, okay. So, but that's how you use incomplete Cholesky. It might be more interesting case like on a larger matrix. Um, so yeah. So basically, what we want to see if we get like a few examples um, of forming a preconditioner using an incomplete Cholesky with some parameters that work, and show that it still converges fairly well.
So what's the advantage of using an incomplete Cholesky to the full Cholesky?
Um, even your Cholesky factor should turn out to be sparser.
Like, because when we did the full Cholesky and we compared it to the full sparse Cholesky, they were the same. They had the same, almost the same sparsity. Like
Um,
maybe a few,
yeah.
one or two items, elements difference.
Well, the thing is, if a true Cholesky factor is sparse, that's great. If you have an example where a true Cholesky factor is not sparse, um, then you want to do incomplete in that case.
So, well, in that case, we'll have to set a high drop tolerance.
Depends on the example, I guess.
I see. Okay.
Yeah. Okay.
We're meeting on Wednesday, right?
Yep.
Okay. Let's see what I will have before then.
Okay. All right. Good luck.
Well, thank you.